Some more data, primary and secondary data. Primary data is data that we collect at its original source. We know it's right because we saw it. Casinos used to have folks who walked around their casino and actually trailed customers. Their job would be to sit by the door, wait till somebody walked in, and then they follow that person around from the time they get there to the time they leave. That's primary data. They know exactly what they did. Now we do that with a card. You put your card in the machine, we know. Secondary data is when you ask them. You don't know for sure. You ask somebody. You get the data from a different source. When I was a little kid, my grandmother got a survey from Nielsen Company that tracks who watches what television shows. It was addressed to my grandmother, had my grandmother's return address and information on it, had my grandma's demographics on it. She filled in the part about age and where she lived and all of that. And then she gave me the form to fill out, which I dutifully did based on the television shows that I watched. The Nielsen Company got secondary data. They had to trust that my grandmother was telling them the truth about what television shows she watched. And the fact that she was watching Star Trek probably interested them because they probably then went to advertisers and said, hey, old people are sitting here watching Star Trek and watching cartoons on Saturday morning. So primary data, we trust, we believe. We see you do it, we measure you doing it, we believe it. Secondary data, we don't believe so much. You may or may not be telling us the truth. And we'll talk about that. We have all kind of a whole chapter on whether or not you're telling us the truth. So some more data. Data type number 1 here is what we call nominal data. That's what we say is categorical. So when we put data into groups, red, blue, green, that's nominal. What's your favorite color? It's nominal data. The value of the data is no number. It's just red, blue, green, male, female. Ordinal data are data that are ranked. So if I tell you, give me a list and give me your 5 favorite music groups or singers in order, you do that. Your 5 favorite movies, you put them in order. Can you tell me how much more you like your first movie to your second movie? So if your first favorite movie is Empire Strikes Back and your second most favorite movie is The Force Awakens, can you tell me you like Empire Strikes Back 2.2 times as much? If your favorite singer is Taylor Swift and your second favorite singer is Katy Perry, can you say, I like Taylor Swift 1.234 times as much as... You can't. So it's ranked data. You can make it sort of numeric where you're going 1, 2, 3, 4, 5, but the rankings don't mean anything really. The numbers don't. Number 3 is what we call interval data. In interval data, the interval has a meaning, but 0 is arbitrary. So temperature is the best example of this, or one of the best examples of this. If I tell you it's 40 degrees outside, you don't know what to wear. Because if it's 40 degrees Kelvin and you walk outside, you're going to freeze to death. If it's 40 degrees Fahrenheit and you walk outside, it's cold and you probably need your jacket, but you're not going to instantly freeze. If it's 40 degrees Celsius, well, now you're wearing your shorts and your t-shirt and you're not really happy about it. 0 in those cases is arbitrary. We set a 0. We know what it means, the difference between 40 degrees Fahrenheit and 80 degrees Fahrenheit. So we know what that difference means. And we know what the difference between 40 degrees Celsius and 80 degrees Celsius means. But we picked a 0. In all those cases, we picked a 0. Another example of that would be altitude. When airplanes fly along, they know 2 different altitudes. They know their altitude above sea level, and they know their altitude above the ground. When a plane lands in Las Vegas, it lands on that runway. Its altitude above the ground is now 0, but its altitude above sea level is about 2,000 feet. the pilot has to know both those things to make sure he doesn't run into the ground, or she doesn't run into the ground. So we set that zero as arbitrary. Sea level is arbitrary. The ground height changes all the time. That's arbitrary. So those are interval data. Fortunately for us, there's very little interval data in the world. Most data in the world is ratio. And in ratio data, the intervals have a specific meaning, and zero means something. If I say, my company made $0 last year, you know what that means. If I say, I have 0 employees, you know what that means. If I say, I got a 0 on the test, you know what that means. So in ratio, I don't have to explain what the 0 is. I know exactly what the 0 is. And most of the data we have fall into that category, and they're ratio data. All right, some very simple things, some words. The whole of anything in a statistical problem is called the population or the universe. A subset of that population or universe is called a sample, and then one individual, whether that's an individual business, an individual person, an individual crayon, whatever it is called that observation. So we have ways of marking these things out. When you see a Greek letter like mu or omega or theta in a statistical analysis, sigma, that means we're dealing with a population. That means we have all of the possible data. When you see good old American English letters, that means we have a sample. So if you see an S as a variable in a statistical problem, that S means that we calculated that data from a subset. 28,000 students at UNLV, if we calculate something using all 28,000 students, you're going to see sigmas or mu's. If we calculate the same data for 100 students at UNLV, then you're going to see an S, because that S is a subset of that whole population, that sample. Okay? We tend to use the letter X to mean one observation. It's tradition. And just because we had these rules, we have one example of something that breaks them, and that is what we call the population size and the sample size. The population and sample size are the number of people, or the number of businesses, or the number of what's in here. So N, capital N, is used for the population size. So there's 28,000 students at UNLV. Our capital N is 28,000. Little n means a sample. So if I pick 100 students and talk to them, that means that little n is 100. Big N would be 28,000. Little n is 100. If there are 100 casinos up and down the strip, that would be big N. If I calculate something using 4 of them, that 4 would be little n. Okay. A number that's calculated from the population is called a parameter. And that's pretty easy to remember because we have the letter P in both. So a number that's calculated from the population is a parameter. And cleverly, a number that's calculated from a sample is called a statistic. And remember the definition of statistics. Statistic is something that has uncertainty. If I calculate a number from all 28,000 UNLV students, it's probably the right number. If I pick 100 students and calculate it from them and assume that that number fits the whole of the 28,000, I might be wrong. There's uncertainty in that. And that's why we call that a statistic. So it's important to remember in statistics that we're never, ever proving something, and we're never saying that something is the truth. Statistics do not give us proof. They do not give us truth. In fact, they don't even give us disproof or untruth. Statistics tell us how likely things are. Statistics tell us this is possible, but statistics are never proof of anything, and they don't tell us what the truth is, which led Mark Twain to say that he thought there were lies, damn lies, and worst of all, there was statistics. It's not really that bad because we can attach numbers to things. We can say, hey, there's a 95% chance that's right, or there's a 99% chance. And having those kind of numbers gives us an idea of whether or not this thing is correct. In statistical problems, we have errors. We try to figure out, we go talk to 100 students and we ask them what their GPAs are, and we get a different answer. That's when we actually check all 28,000, it doesn't quite match. Or we go talk to 100 voters and we ask them who they're gonna vote for, and then when all 130 million people go vote, it doesn't quite match up. It's an error. It's statistics. It's not unusual. It's not uncommon. It's not unnatural. It's just the way the world is. Our problem is that there are two kinds of these errors. One kind of error is a bad kind of error, and we call that bias. Bias is when we get the same error over and over and over again. If you go and talk only to Republicans and ask them who they're going to vote for, you're never, ever going to get an outcome which matches the outcome of the actual election. You have a bias created by the fact that your group that you're talking to, your sample, isn't representative of all the voters. On the other hand, if you pick 100 people and they are pretty much spread out across all the voters and very representative, you're still going to get a different answer every time you talk to them. Things are going to change, your people are going to change, the number's going to go up and down a little bit. We call that variability. Variability is natural, normal, and in fact, it's what makes life interesting. Our life is interesting because when we get up in the morning, it doesn't take us exactly the same amount of time to get to work every day. Some days it's nice and clear and there's hardly anybody on the road and we zip into work. Some days there's an accident. Some days it's raining. Some days we get behind some truck and we just can't get around them. That variability is, again, natural, normal, keeps us from getting bored. Bias would be that you know there's always a truck in this lane, and yet you drive down that lane with that truck in it every day anyhow and get to work late. Variability is you leave in enough time to get to school or get to work, and sometimes you make it on time and sometimes you don't. Variability, normal. Bias, something we need to make sure we don't have. So here's a beautiful picture of it. We have 3 sets of 4 darts. We're throwing darts at a dartboard and we're trying to get in the bullseye. And you notice we have 4 darts right here in the middle that all hit in the same spot in the bullseye. Those 4 darts don't have bias and they don't have variability. They're all in the same place. They're all pretty much the same. These 4 dots up here, the red dots, they're all in the same place, but it's not the right place. Those dots have a bias. If I'm aiming for the bullseye here in the middle and I get always high and to the left, I have a bias. And in fact, I can fix that because if I want to hit the middle, all I need to do is come down and aim over here. And if I'm always high and to the left, now I'll start hitting the bullseye. So these guys have no variability, but they have bias. The 4 other blue dots, if we average them, they're on top of the bullseye. They're just all a long ways from the bullseye. They don't have any bias. They're still centered on the middle of the dartboard, but they have a lot of variability. They're spread way out. Okay? So dots in the middle, no bias, no variability. Red dots, bias, no variability. Other 4 blue dots, no bias, lots of variability.